the determinant of Laplacian on a Riemann surface, on a compact Riemann surface. So the Laplacian, of course, has infinitely many eigenvalues. So this has to be regularized. And there's various ways to do that. The standard way is to make a zeta function out of the eigenvalues. So you make an analog of the Riemann zeta function. This converges for real part of S large enough, and under mild conditions on the lambda k, it analytically continues. So you can make the regularized sum, the regularized trace, as zeta of -1, and to make the regularized determinant, you just need to take the exponential of the derivative at 0, of negative the derivative at 0. And the important features of this regularization is that it behaves correctly if you split off finitely many eigenvalues, and it behaves correctly if you make a small change. So if you modify each of these by some epsilon k, where the epsilon k's actually converge, then the product splits. Where it doesn't behave the way that you think it would, or you might hope it would, is that if you split apart infinitely many eigenvalues out of this regularized product, then it's not necessarily true that the products of the two sets of eigenvalues is the regularized product of the entire set. So it's not necessarily true that determinant AB is determinant A times determinant B. So then a trivial case, I guess, is on the circle. Where we can write down the eigenvalues explicitly. The next harder case is on a surface. If we take a conformal structure in the equivalence class of the metric, the change within a conformal class is fairly well understood. So it makes sense to restrict here to metrics of constant curvature. And again, the genus 0 case is fairly trivial. We know all the eigenvalues explicitly. So the first non-trivial case is the genus 1 case. So here, of course, the Laplacian I'm talking about is the Laplacian for the metric we're talking about. So for genus 0, it's the spherical metric, and in genus 1, it's the flat metric. So if we normalize the area of the torus to 1, then the determinant of the Laplacian is the imaginary part of the tau, which defines the torus times the Dedekind function of tau, its modulus to the fourth, where the Dedekind function is this classical modular form. And the q is e to the 2 pi I tau. So if you take the exponential of this picture, rather than modding out by this lattice, you're modding out by, so here the torus is, I've written it up here, is modulo this lattice. You can also make it modulo multiplication by q. So So then the next result on this after that is in the 1980s when physicists were concerned with this for string theory. And really, everything that I'm doing is sort of catching up with what physicists were doing in the mid-80s. So the result of Doker and Fong in 1986 is that this determinant is actually given by a very similar product to the Dedekind function, which is the Selberg-Zeta function for this surface. So in the hyperbolic metric, you have closed geodesics. If you look at just the primitive closed geodesics, so ones that aren't a multiple of another geodesic, and take this product of 1 minus the norm of the geodesic to the m plus s, where the norm is e to the minus length of the geodesic. So in a sense, this seems like a complete solution to the question of what the determinant is for a hyperbolic surface. But in a sense, this formula is a little unsatisfying because this is highly connected to the holomorphic structure on the moduli space of surfaces. So here, this is a holomorphic modular form. Whereas here, we don't have sort of any connection. The space of Riemann surfaces of G greater than 1 is a complex manifold or complex orbifold. And this this product is sort of unrelated to the complex structure. It doesn't respect the complex structure at all. It's strictly a real formula. It's a geometric. This occurred to originally to Belavin and Konizhnik, also in '86. Their heuristics were that the determinant of the Laplacian on a Riemann surface, you don't have the two pieces where it goes up and down. The Laplacian on a Riemann surface is just d bar times the adjoint, and the determinant of the adjoint should just be the conjugate of the determinant of d bar. So if these were finite dimensional operators, you would have the determinant of Laplacian would be determinant of d bar times determinant of d bar star, which would be the complex conjugate. And the determinant of d bar doesn't involve the metric at all. The only part of this that's not, when I say holomorphic, I mean holomorphic dependence on moduli. The part that's not holomorphic is when you're introducing the metric. And so determinant of d bar should, on moral grounds, be a holomorphic function on the moduli space. Given that this is not a regular determinant but a regularized product, there's going to be some sort of correction factor here, what they call it an anomaly. So this was called the holomorphic anomaly for the Laplacian. And I should emphasize that this picture was just heuristics. In particular, d bar goes from one space to another, so we don't have an actual definition for determinant of d bar. But on a on the level of physical heuristics, this was what was expected to happen. What they did prove on the mathematical level is some information about this anomaly. So if if this was true without the anomaly, then if you take log and dd bar here, this would be log dd bar log of modulus squared of a holomorphic function. That would be 0. So if this worked out perfectly, you would expect that dd bar of log of this quantity would actually be would be 0 here. So that this is expressing dd bar log of the anomaly. Here we're working on the moduli space of genus G Riemann surfaces. The mu and nu are tangent vectors, and the WP is the Weil-Petersen metric. On a Riemann surface, on a point on the moduli space, a tangent vector to the moduli space is represented as a -1,1 form, or Beltrami differential on the Riemann surface. And so then the Weil-Petersen metric of two Beltrami differentials is So that's dependent on using the hyperbolic metric. So what this suggests, there's a little bit to prove here that this actually integrates, but that this formula is correct, where the anomaly here is the exponential of. This is something called the classical Liouville action. The relevant feature of this thing is that it's a Kähler potential for the Weil-Petersen metric on moduli space. So this is an extension. Quillen in '84 found a very similar result for families of D-bar operators, but he looked at linear families, so fixing the Riemann surface and taking a linear family of Cauchy-Riemann operators. And this is the analogous result for a family of Riemann surfaces. The extension of Takhtajan-Zograf was to actually get an explicit expression for this classical Liouville action. By physical heuristics, it should be this integral. What makes it difficult is that this integral is not well defined. If you do it over a fundamental domain, this is not an area form on the surface. So you have to do some sort of trickery with boundary terms to make this well defined. But if you just go through formally and find the pretend you're a physicist and do the formal variation of this, you find that you end up with the Weil-Petersen metric here. So then the so to put the genus 1 result in the same format to compare, if you calculate the Liouville action for a torus, it's a flat metric, so it's somewhat simpler. And so we have this expression for the determinant of the Laplacian on a Riemann surface. And then this is the expression in genus greater than 1. So this result is a closer analogy to the genus 1 result. In particular, the determinant is some holomorphic anomaly times modulus squared of a function which is, this is holomorphic on the moduli space of Riemann surfaces. So this is, in some sense, respecting the holomorphic structure of the space of Riemann surfaces. And so then you might say, well, if this is the essentially Dedekind eta function here, what's sort of the analog for Dedekind eta for higher genus? And to explain the result for this function, I have to just remind you about just some definitions for uniformization. So I want to represent the Riemann surface as CP1 modulo a subgroup of PSL2C. Each element in that group is, if you conjugate its fixed points to 0 and infinity, then it's conjugate to multiplication by some complex number. And if I'm just working with a compact Riemann surface here, all of the elements are hyperbolic. So these we can assume that these complex numbers, the n gammas, are well, if we're doing the standard Fuchsian uniformization, these are hyperbolic, and so they would be real and between 0 and 1, strictly between 0 and 1. In more generality, they'll be loxodromic, so not necessarily real, but with modulus between 0 and 1. So then the two uniformizations that I want to use are the standard Fuchsian uniformization, which is taking the upper half plane and giving x as a quotient of the upper half plane, and this is the uniformization which gives you the hyperbolic metric on x. And so this is the uniformization in which the spectral theory is simple. We can write down the Green's function for the Laplacian. In terms of working with the eigenvalues of the Laplacian, this is the correct uniformization to use. And it's worth noting at this point that the Selberg zeta function, which is in the Dokern-Fong result, is how the determinant of Laplacian is written. Rather than e to the minus length of geodesics, you can think of these numbers as being multipliers for the group elements that define the surface. So the determinant of the Laplacian is a special value of this zeta function, where the zeta function is written in terms of multipliers of the group elements for the Fuchsian group uniformizing the surface. The primitive geodesics correspond to primitive conjugacy classes in the Fuchsian group. Now, on the other hand, this uniformization is not very nice for holomorphic structure. If you think of the uniformization as being a family of projective connections, it's not a holomorphic family of projective connections. In other words, if you think of the Teichmuller space of Riemann surfaces as being a family of Fuchsian groups, Then the parameters for your space are the fixed points for each element of your group, each generator, and the multipliers, and all those are real numbers. So this doesn't respect the holomorphic structure at all. But it's the correct uniformization for the spectral question. On the other hand, a nice uniformization for holomorphic purposes, although not very good for spectral purposes, is the Schottky uniformization, where topologically what we're doing here is we're taking the Riemann sphere and then gluing a handle here and a handle here. So this would be a genus 2 surface. That gluing is taking place by some subgroup of PSL2C. So in this case, it's a free subgroup of PSL2C, mapping pairs of circles to pairs of circles. So the fundamental domain here is the yellow region outside those circles, and the Riemann surface is the ordinary set for that group, modulo this free subgroup of PSL2C. So then, in this uniformization, the hyperbolic metric would be very complicated, or at least not explicit. But this uniformization is a holomorphic family over the Teichmüller space. In other words, you can take the fixed points and multipliers for these generators. So here we've got 2 generators for the group for a genus 2 surface, and each of those generators has 2 fixed points and a multiplier. The 2 fixed points and multiplier are all complex numbers, and so you can take those 6 complex numbers as parameters for your space of Riemann surfaces. If you do that, you get a quotient of the Teichmüller space, which is called the Schottky space. So the space of Schottky groups of a fixed genus G is a quotient of the Teichmüller space of Riemann surfaces of genus G. So now, the Docker and Fong result is that the determinant can be written as a special value of the Selberg zeta function, which is this product over multipliers for the Fuchsian group. But what's a little, I think, more faithful to the genus 1 result is this result of Zograf, that in fact the determinant is the holomorphic anomaly times modulus squared of a holomorphic function. This holomorphic function is sort of an analog for the Dedekind eta, and it's actually the exact same product as for the Selberg zeta, except the multipliers here, instead of being taken to be the multipliers for Fuchsian group, these are taken to be the multipliers for the Schottky group uniformizing the surface. So this implies sort of, to me, a surprising relation between the Fuchsian and Schottky uniformizations that we can just equate these two. So this zeta function taken over multipliers for the Fuchsian group is equal to modulus squared of another zeta function taken over multipliers for the Schottky group times this holomorphic anomaly term, times this Liouville action. the Liouville action there can be thought of as coming from given a Schottky uniformization. One can so one has a fundamental domain for a Schottky uniformization. And then that fundamental domain is itself a hyperbolic Riemann surface. So you can take the Fuchsian uniformization of that fundamental domain. So you can take a cover of the fundamental domain for the Schottky group, or the ordinary set of the Schottky group, by the hyperbolic plane, and the derivative of this Liouville action is derivative in the moduli space is a Schwarzian derivative of this covering map. Another way of seeing this thing is that it comes out of the regularization. But let me come back to that in a minute. So then, oh yeah. Incidentally, this Liouville action, I was saying that it's this integral plus some boundary terms. The boundary terms are defined in terms of the Schottky uniformization for this group. So it's an integral over the bounding circles on a fundamental domain of this sort of horrible looking expression where the LKs are the generators for the Schottky group. And there's a better way of looking at this, which I'll come back to in a second. Yeah. Oh, CLK is LK. Each LK can be written as a 2x2 matrix, and so the C is the C entry for that 2x2 matrix, which is geometrically a very odd thing. So then our extension of this, the work of physicists was always concerned not just with the determinant of Laplacian, but the Laplacian on the nth power of the canonical bundle. So so we're working on the nth power of the canonical bundle, which, if you're thinking classically, it's n differentials. These have a natural inner product induced from the hyperbolic metric, so they have a Laplacian. The Laplacian is again sort of heuristically d bar times the adjoint of d bar. Well, it actually is d bar times adjoint of d bar, and heuristically you expect the same factorization formula. The Docker and Fong formula, the Fuchsian formula, is exactly analogous to the case where n is 1. It's a special value of the Selberg zeta function at n. The Belavin-Konishnik result was for the Laplacian on the nth power of the canonical bundle, and this was their expression for dd bar log of the holomorphic anomaly. So again, you get the holomorphic anomaly is again a Kähler potential for the Weil-Peterson metric on the Teichmuller space times some Bernoulli polynomial. And so then the question is, what is the corresponding thing to this analog of the Dedekind eta function? What's the explicit expression for this function? And as it turns out, it's again analogous to the Dokern-Fong result, which is just that for the nth power of the canonical bundle, it's just the special value at n. It's almost the same thing here, that it's the same function that we had before, but the special value at n times a certain regularization factor. The reason for the regularization factor is, normalization factor. The reason for the normalization factor is because some sort of normalization has to be made for the kernel of this operator. I should go back and say that, of course, the easy answer to this, to what this determinant is 0, because it always has a kernel, right? So the prime here represents that I'm taking it on the orthogonal complement to the kernel, and so it's necessary here to divide by the determinant of the matrix of inner products for a basis of the kernel. And so for n equals 1, you have the classical normalization for abelian differentials, and you have to make an extension of that normalization in order for this to work. And so depending on the parameters you take in the extension, you get some extra factors in this zeta function. Sort of introduces extra Euler factors. So, and then you can say, well, what's special about Schottky groups? Well, Schottky groups are nice because they do form a holomorphic family of uniformizations over the Teichmuller space. The other class of uniformizations that also form a holomorphic family are the quasi-Fuchsian groups. So a quasi-Fuchsian group, the exact definition is that it's the conjugation of a Fuchsian group by a quasi-conformal map. But the intuitive idea is that if you take a Fuchsian group and then you move any of the generators, allowing the generators to become complex, you get a quasi-Fuchsian group. So quasi-Fuchsian group, Fuchsian group, when you make a Riemann surface as a quotient of the upper half plane, the group is always acting on the upper half plane plus the lower half plane. So really, when you uniformize, you get your Riemann surface disjoint union with a mirror image of the Riemann surface. So in a quasi-Fuchsian group, you've allowed a distortion such that this surface is no longer the mirror image of the other one. So the quotient of a quasi-Fuchsian group, of the ordinary set of a quasi-Fuchsian group by the group, gives you 2 Riemann surfaces. And the simultaneous uniformization theorem of Baer's says that given any 2 Riemann surfaces with the same genus, you can find a quasi-Fuchsian group which simultaneously uniformizes those two surfaces. So you might expect that if this result is really only dependent on the on the holomorphic character of the Schottky group, then the same thing should hold for quasi-Fuchsian groups. The determinant of the Laplacian on the surface, here it really should be the determinant on the quotient surface, which is the disjoint union of x and y. So it should be a product of determinants for x and y. And what's the Liouville action? Well, Takhtajan and Cho wrote a paper where they extended the Liouville action was defined for Schottky groups, and they extended it for a large class of Kleinian groups, including quasi-Fuchsian. And so the result that you would expect holds. So if you form this zeta-like product for a quasi-Fuchsian group, the modulus squared of this is this holomorphic anomaly factor, this exponential of a Kähler potential for the Weil-Petersen metric. Here this is a Kähler potential for the Weil-Petersen metric on the quasi-Fuchsian deformation space. What you get is a product of determinants for the two Riemann surfaces, divided again by the determinants of the matrix of inner products for a choice of basis of the kernels in each case. So I should emphasize here that that neither of these theorems are proved in the way you might, well, the way I might hope. The Docker and Fong result, they proved it by explicit computation of heat kernels, and you can, and basically they reprove the Selberg trace formula, and so you can get this result as a corollary of the Selberg trace formula. So you're explicitly taking the integral kernel here and sort of unfolding it over the group, and so that is fairly explicit. Our result for Schottky groups is obtained by making the right guess for the formula, and then taking the variation of both sides and just showing that the variation of both sides is equal. So we don't have really a good handle on this is not proved by a Selberg trace formula kind of an argument. It's proved by making the right guess, well actually making the wrong guess and having some terms left over and then trying to figure out what those are the variation of. But it's just a variational result. And similarly, the quasi-Fuchsian case is again not done explicitly as a trace formula. It's taking the known result for Fuchsian groups and then writing down an extension for that to the quasi-Fuchsian space, and using an extension of the Schwartz reflection lemma to say that the fact that this is correct on the subspace of Fuchsian groups, and that it has a certain reflection symmetry when you replace the group with its conjugate, forces that to be true throughout the quasi-Fuchsian space. What's suggestive here, and what I think suggests that it should be sort of a trace formula argument, is this is a bit of a strange zeta function if you think of it on the Riemann surface. It doesn't correspond to any of the sort of Ruel type family in a direct way, but it is kind of a at least plausible looking zeta function. If you think of this as a function on the rather than on the Riemann surface, on the three-manifold. So the Schottky group, the subgroup of PSL2C, also acts on the upper half space, H3. And in terms of that, these multipliers, the multiplier is a complex number. Its modulus is the length of a closed geodesic, and its argument is on the orthogonal complement to a point. If you look at the twist under parallel translation, that's the argument of the n gammas. So in analogy to the Selberg zeta function, where these were e to the minus length of the closed geodesics, this is a complex number whose modulus is, e to the minus length of the closed geodesic, and the angle, the argument is a twist parameter. Krasnov and later Krasnov and Schlenker have, and also Takhtajan and Cho have interpreted this very horrible-looking Liouville action on the Riemann surface, or on the Schottky group, as actually being a sort of regularized volume for this three-manifold. So the three-manifold is an open, infinite volume hyperbolic manifold. And it's possible to define a regularization of its volume. And that regularized volume can be shown to be the same as the Liouville action there. And in that respect, this this term starts to look like the identity term in the Selberg trace formula. But that is something which I have yet to work out. So the what I wanted to talk about this afternoon, then, if there's any interest in that, is how you can use Teichmuller theory to do these variational arguments for some sort of spectral quantities. So how you actually address those sort of calculations. So that's really it for now. Thanks.
I have a question. For your formula in the case of Kaji-Fukusan case, is it possible to calculate the second derivatives of the left-hand side of your formula with respect to the tangent vectors to the moduli? Can give rise to Bay-Peterson like is this one?
Yes.
Yeah.
Yes. Yes. I haven't done it, but it should be straightforward to do that. Yes.
Oh, really?
That's essentially done in a different version. That's in Takhtajan and Cho's paper. They did a computation equivalent to that to show that the function they define, the S, is actually a Kähler potential for Weil-Peterson metric on the quasi-Fuchsian deformation space. But right, by doing what you suggest, this would give an alternate proof for that. Yeah. It's an excellent question. I don't know. I'd love to know. I don't. It's it's, in our argument, it doesn't happen naturally as a section of a line bundle. There's one way of looking at it in which the function over the Schottky space represents an isometry of line bundles, so giving rise to just a complex valued function on the Schottky space. But as to how it transforms, with respect to the fundamental group of the Schottky space, I don't know. That'd be very interesting to know, because of course the Dedekind-Ita function in genus 1 has very nice homomorphic properties. So it's a great question. I don't know the answer.
So you are working only for the Schottky coefficient case.
Yes.
I wonder whether the terms on the right side could be defined for arbitrary.
Right. That's a very interesting question. So this product is perfectly for n bigger than or equal to 2. It's perfectly well defined for any geometrically finite Kleinian group. For n bigger than or equal to 1, as long as the Hausdorff dimension isn't too big, it's perfectly well defined. This is also well defined for a large class of Kleinian groups, and so we're free to make the right side of that equation. The heuristics seem to break down for the left side, and also our methods break down for the left side because we don't have any more holomorphic family. So we really depend on, when we do a variational argument, on the fact that we're varying with respect to, for example, these n gammas, which are holomorphic functions on the space of Schottky groups. But if we're working with a different family of Kleinian groups, I guess the methods that we're using don't work, and I suspect that we won't get exactly the determinants, but what we will get, I'm not sure.
So I guess your argument basically variation argument.
Right.
To show the variation of the two sides of the same.
Right. And we really depend on the fact that I'm not explaining that correctly. Maybe I can try to answer that better later. But I would be very interested to know what would happen for other Kleinian groups. But it wouldn't be a direct extension of the method we use.
No more question or comment? Okay, then let's try, okay?